Okay, the next theorem that we're going to talk about is called the mean value theorem. And the mean value theorem has a history that dates back probably to maybe the late 1300s to mid 1400s or so. It was actually a couple of mathematicians in India that probably first stated this theorem. And this was probably even predated calculus. But anyway, at any rate, it wasn't until the late 1800s or maybe early 1800s that some French mathematician by the name of Cauchy, actually formally stated this theorem. And you can go back a little bit, and if you know a gentleman by the name of Rolle's theorem actually came up with a special case, a restricted case anyway, of this mean value theorem. But here's what it is. All right, I'm going to give you the in a nutshell conceptual understanding. There's a point on the graph where the slope of the secant equals the slope of the tangent if the function is restricted. So we have two endpoints, and that's what I mean by restricted. There is a point C where the slope of the secant, this is the secant line right here, equals the slope of the tangent. So that's what the mean value theorem says in a nutshell. Okay, so in a nutshell, that's what it says. All right, so here is the mean value theorem. Let's go over the requirements. Number one, the function has to be continuous on a closed interval. That's the first and foremost, the most important part. All right, second part, it has to be differentiable. That means we have to be able to take the derivative on the open interval from a to b. So once those two requirements are met, there is some number c where f prime of c equals f of b minus f of a over b minus a. What it is that the slope of the secant equals the slope of the tangent. All right, that's the nutshell of this great and wonderful idea in calculus. So let's go ahead and take a look at a couple of examples. The first one, not necessarily really involved. The second one, a little bit more challenging because of the fact that it deals with fractions, or a rational function, I should say. But let's take a look here at this problem that we're going to call number 3. All right, so let's see here. What do we know? Well, this right here is a polynomial. All right, it's just a given. It's a polynomial. What can we say about polynomials? Okay, let's write this down. F of x is a polynomial. So this takes care of the most important parts of the theorem. And that is to say that because it is a polynomial, it is actually continuous and differentiable everywhere. So give me a chance to write that down. So it doesn't matter that we're restricted to this interval. Anywhere we're going to find that it's actually continuous and differentiable. So 1 to 3, 2 to 4, anywhere you're looking, it's continuous and differentiable. The conditions are met, in other words, for the theorem. So we can go about taking the derivative, all right, because that's the next part. It's that the derivative, the slope of the tangent equals the slope of the secant. But the only way to find that is by first finding f prime of x. So let's find f prime of x here. F prime of x equals, derivative of 4x squared is 8x minus 1. And then derivative of negative 6 is 0. So 8x minus 1. And now what we're going to do is find f of b minus f of a over b minus a, which is f of 3 minus f of 1 over 3 minus 1. Okay, so we plug that in. We get something that looks like this. So bear with me as I write it all down. And then you're welcome to work all of this out on your calculator if you wish. All right. We end up with doing all the math, 27 minus negative 3 over 2, which is 30 over 2, which is 15. So there's not much left to do here. What we're going to do then is we're going to say, okay, well, now we have the derivative, f prime of x, and set it equal to 15, and then we solve for x. So we're going to add 1, 8x equals 16. You divide both sides by 8, x equals 2. So we're going to say then that our value c, that's guaranteed by the theorem, is 2. So c equals 2 is the value, and that's what I write as my justification, is the value guaranteed by the mean value theorem, and I'm going to abbreviate MVT. It's very common in a lot of books. The MVT, where f prime of c equals f of b minus f of a all over b minus a. So that right there is what's going on with this there. So that's the first question, really nothing to it. The second question, like I said, a little more involved. So you might want to pause right now, rewatch this video, this first part of the video, before we get into the more intense problem. All right, so stick around. Okay, now we're taking a look at this next example, f of x equal x minus 1 over x plus 2 on the interval from 0 to 2. Well, it's a rational function, and it's important to note here that the domain restriction is actually x equals negative 2. All right, so what I'm going to write here is that f of x is actually continuous. Let me erase this. Continuous is actually, I should say, f of x is not, that's the important part, not continuous or differentiable, and I have always shortened that, it's too long to write, at x equals negative 2, which is good for us because it's not in the closed interval from 0 to 2. It doesn't exist there. That's good. So what we will say is that we can find a value we'll call c, where the derivative equals the slope of the secant. That's what this is saying here. All right, so there is a place we just got to take the derivative, and the derivative is actually not even the hard part. The hard part, I think, is solving, but it's not that difficult. All right, so we have to use the quotient rule. All right, so here's high, if you know the quotient rule, and here's low. And the derivatives there are actually really nice. It's just 1 in both cases. So we say low d high, which is if we find f prime of x, low d high is x plus 2 times 1. So that's just x plus 2 minus high d low, which is minus an x minus 1 over low, which is x plus 2 square. All right, so we end up with x plus 2 minus x minus 1 over x plus 2 quantity square, and we find that the x's actually cancel, and actually this is actually plus 1 now that I see it when you distribute. Okay, so we end up with something like 3 over x plus 2 square. All right, that's my derivative. Now what I need to do is I need to find the slope of the secant by plugging in the 2 and the 0. So this part can get tricky if you're not careful, but it's not that bad. So you end up with something like 2 minus 1 over 2 plus 2 minus 0 minus 1 over 0 plus 2, all divided by, what is that, 2. Okay, So you end up with something like 2 minus 1, which is 1 over 4, 1/4, minus a negative 1 over 2. And that actually becomes plus, all divided by 2, which you end up having something like 1/4 plus 1/2. That's just 3/4 divided by 2. If you've taken my class before, you know when dividing fractions, always remember 2, KFC. So 3/4 gets multiplied then by 1 over 2. Keep the first, flip the second. So 2 becomes 1 over 2. Change the sign from division to multiplication, 3/8. All right. So not much more to it other than solve. So what we're going to do is take the derivative, 3 over x plus 2 square, and we're going to equate it, set it equal to 3/8. All right. So what I would tell you is kind of do this. My students have said butterfly. It's this cross multiplication. That's all that it is. All right. You end up with 3 times x plus 2 quantity square equals 24. You divide out the 3, divide out the 3. You end up with something like x plus 2 quantity square equals 8. And then you go about solving this kind of a quadratic by applying the square root property. All right, that's not terribly intense. You end up with something like this. X plus 2 equals plus and minus. Yes, plus and minus. The square root of 8, which the square root of 8 is square root of 2 times the square root of 4. That's 2 square root of 2. So plus and minus 2 square root of 2 is what we have there. And then we subtract 2 on both sides. Gets rid of that. X equals negative 2 plus 2 square root of 2. And x equals negative 2 minus 2 square root of 2. So roughly evaluated on a calculator, you're going to get something like, I don't know, 0.828. And on this one, you're going to get something like negative 4.828, I believe. All right, well, clearly we know our interval was from 0 to 2. So this one right here is in the interval from 0 to 2. All right, and remember at the beginning of the video, I told you it depends on the interval, but there could be multiple places where the derivative is 0. Or I'm sorry, where the slope of the tangent equals the slope of the secant. Actually, maybe not this video, but anyway, maybe I'm just speaking too fast. All right, this one right here is not in the interval from 0 to 2. All right, so we know we're not going to worry about this number, but we are going to worry about this number right here. All right, and so to sum all of this up, we're going to say then we have found our value c. It is negative 2 plus 2 square root of 2. All right, this is the value. This is the value guaranteed by the mean value theorem. All right, by the mean value theorem, MVT, where, and again we say f prime of c equals f of b minus f of a over b minus a. In a nutshell, there is a place, this is the place, negative 2 plus 2 square root of 2, where the slope of the tangent equals the slope of the secant. Nothing more to it. All right, so I hope this gives you a better understanding of the mean value theorem, really gets to the meat and potatoes of it. In a nutshell, I already mentioned it. Slope of the secant equals the slope of the tangent. If it's helpful, remember, like and subscribe.